for alternate, we can have alternate mixing strategies instead of using the inverting amplifiers or the single pole double throw switches, which are being controlled at the rate of local oscillator frequency, in order to produce a pulsating positive VIN and negative VIN outputs. Well, we can use a center tap transformer. For example, in this configuration, you see you have an RF input in series with the center tap transformer. Now, what happens is that, for example, once this is alternating, but this is plus minus, you have two AC sources on the secondary side that turns the coil N2 and N3. So it's like positive, negative, and you have the node voltage V1. So you're going to have a current produced like this. Then over here it goes like this in this fashion, and so you see the net flux and the net current at the center tap, the return path, which also happens with the return path of these two currents, is zero. So there's the V out produced at the center tap is zero, owing to the two separate sources. So what you're doing using a center tap transformer is you're inverting, you're creating a phase inversion of V1 over here. So for example, this V2 will be equal to minus V1, and there will be no output. So these two are two separate AC sources which yield zero output at the load. So this is what happens when you simulate the circuit. This is an ADS schematic, and a single tone harmonic balance simulation is carried out. And what happens is, as expected, you see we have this V1, V2, which are pi radians out of phase, exactly out of phase, and then they cancel at V out. This pink line shows that the net flux is being cancelled at center tap. So the necessary phase inversion provided at the nodes V1 and V2 by the center tapping of secondary side is being illustrated and the simulated output. So you note that the V out is again V1 plus V2, so there is no output due to the phase inversion. So how we use this center tap strategy is we create two phase inverted voltages V1 and V2, and we use them to, for example, over here, just like what we have seen before, we have this, we can create alternating minus VIN, plus VIN, minus VIN, plus VIN, since we have those two inverted phase voltages. And if a switch can be controlled at the rate of local oscillator frequency omega L, well, then you can have a square waveform like this. So again, you see, if you have a this single pole double throw switch, you have two ports from which the switching is being done. So you can have VIN, you can have minus VIN. So I mean, instead of using the inverting amplifier, you can use a center tap transformer as well. You can use a center tap transformer to create the necessary phase inversion, and then switch the do the switching at the frequency omega L to produce the mixer output, which is again a series of plus VIN and minus VIN, plus VIN and minus VIN. This is an alternate strategy using center tap transformer. But again, this is the output. The output is still a modulated or a mixed waveform, where VIN is mixed with the square waveform or square local oscillator waveform, resulting in a shift of the input signal at the fundamental and odd harmonics, just like before. So I mean, this output, which consists of VIN and minus VIN, which is the output of this switch from the center tap transformer, it again consists of offsets, not only at the fundamental but at the odd harmonics of the local oscillator frequency omega L. Now, the alternatives, I mean, these are all alternative strategies. The equivalence is shown in yet another circuit over here. You see, instead of using a single pole double throw, you can have a single pole, single throw switch. So there is only one port over here, and you can still control the switching by local oscillator frequency. And for example, over here you have a positive V in, you have a positive in. This is positive. This is negative. You again have an AC cycle. This is a positive. This is positive. This is negative. This is positive. So you have two AC sources from a center tap transformer. Again, nothing returns at the center tap. So this is effectively ground. So you can have a V in, and then alternative this switch is open. When this opens, when this switch opens, this switch closes, you will have, when this switch is closed, you will have positive in. When this switch closes, the bottom switch closes, you have negative in, and this again, this trend continues. So this is again an alternate strategy. You can replace a single pole double throw switch which has two ports by a single pole, single throw. Uh, Alternatively, you can have active mixers. So if you are implying FET devices transistors, which can be controlled by a gate source voltage. These are voltage controlled devices. Unlike BJTs, which are current controlled devices, you can have active mixers. So mixers based on transistors are called active mixers. So basically, what they're doing is it's a switching operation of the top transistor and the bottom transistor. So the necessary phase inversion is being provided by the local oscillator. So only one transistor is switched on. So you see this second center tap transformer that provides the LO phase inversion, the local oscillator phase inversion, so that one FET is turned on while the other is off. So you can have this mixing of the local oscillator current with the RF current, and then you have a positive vein. And similarly, when you have a negative vein, this is switched through from through the bottom FET, the transistor, to produce minus vein. So again, you have the output like this: plus vein, minus vein. So you can use active mixer strategies as well to produce again a square train of input voltage like this.